Hi, everyone. Thank you so much for coming to what I hear is the last Blackboard talk for CITA in 2024. This Blackboard talk has two goals. I think two is sufficient for 1 hour. The first goal is to discuss ISM turbulence to some degree, as in what drives the turbulence in the ISM, what kind of plasma the ISM is for the plasma physicists. And also, I want to essentially go through a method, a statistical method for measuring energy flux between different K modes in the turbulence. And if this doesn't make sense right now, I'll hopefully make it very clear as we go through the talk. So the title of this talk is supernova-driven turbulence in a multi-phase ISM. And essentially, I've called it this because I'm going to be solely discussing supernova driving turbulence. There are many mechanisms that drive the turbulence in the ISM, but let's just first talk about ISM as a plasma and what it's all about to begin with. So the ISM is a multi-phase plasma. So what does multi-phase mean? What do I mean by multi-phase plasma? You can tell me. Yes? Exactly. So it's a plasma that has a whole range of temperatures coexisting in some stable and unstable forms. And I think a beautiful way of seeing that the ISM is a multi-phase plasma is essentially drawing out its phase space. So this is pressure, this is density, and if I draw a straight line through this plot where essentially the cooling and the heating are balanced, so this is at constant pressure, then there are a number of intersections on this plot. And this ends up being a stable phase of the ISM, this ends up being a stable phase of the ISM, and this ends up being an unstable phase of the ISM. So this is something that I'll talk about in a little bit more detail. Now, it's a collisional plasma as well, so the mean free path is much smaller than the system size of all of these kind of fluctuations of different equilibria. So this is very different from the high energy plasmas that Michael deals with. And it's a turbulent plasma. So what's something that comes to mind immediately when someone talks about turbulence? What kind of parameters should we be discussing if we're talking about turbulent plasmas? Yeah? What was that? I heard a murmur. Well, I wouldn't say Mach number, I would say the Reynolds number and the magnetic Reynolds number. And that is because the Reynolds number is, of course, defined as essentially this is a new Laplacian. So I went through this last time in my talk, but the Reynolds number is really defined as essentially the strength of the nonlinearity from the hydrodynamical equation. So this is the thing that gives rise to all the nonlinear structures in your hydrodynamics versus the dissipation. So in other words, if the Reynolds number is very large, you're going to be dominated by all these nonlinear features in your plasma. And if the Reynolds number is very low, you're going to be dominated by just viscosity killing off all these nonlinear features. So there's another one that I'm not going to talk about too much, but it's the RM, which is exactly equivalent, but for the magnetic field. So these are the two parameters that you should always be thinking about when someone talks about turbulence. These ought to be very large. And if they're not large, then this flow is going to be viscous dominated and it's not going to become turbulent. So let's talk about some of the parameters for the phases, some of these phases that I mentioned here. So we have the hot ionized medium. So this is a very hot, unstable phase of the ISM. It's very hot. So this is greater than 10 to the 6 Kelvin. And this is the unstable phase of the ISM. So really it's cooling, but the cooling time is so slow, actually like a giga-year cooling time, that this phase just kind of exists. It hangs around. And this is like, you know, all of the hot plasma that's being blown out in the winds of the galaxy and so on. So the typical size scales for this is around, I mean, the kind of characteristic HIM blob is around 100 PC. It's hot. And of course, that the Reynolds number is proportional to something like T to the minus negative 2.5. So it's actually really quite viscous, and it's one of the most viscous phases of the ISM. It's only around 10 squared, or so 100, RE 100. So it's not very turbulent at all. And it's quite dilute. So let's put this down here. Now RM, again, RM is just essentially the same thing. Instead of U here, you're going to have the magnetic field over the ohmic resistivity in this case. Of course, there's other RMs for different kinds of resistivities. You know, you could have ambipolar diffusion down here. And this is just kind of like this. This is my diffusion coefficient for the magnetic field. RM is actually very, very large here. And that's because RM scales like. So essentially, these very, very hot plasmas are going to have quite low REs, but quite high RMs. And this is 10 to the 22, which in my world is fundamentally infinity because we can never simulate such a high RM. Now let's go down. We go from the hot ionized medium to the warm ionized medium. So we're getting down to temperatures around 10 to the 4-ish. Number density is 10 to the negative 1, so we're becoming denser. RE is skyrocketing now. We're going from 10 to the 2 to 10 to the 7, and 10 to the 7 I can actually do on a computer, so this is no longer infinity for me. 10 to the 7 is actually possible to do. 10 to the 18 is impossible to do. And we're also getting smaller in size scale. So in your mind, you should kind of be thinking about these blobs that are kind of nested within inside of each other. We have the HIM out here, and we have the warmer mediums down here on smaller length scales. Now, of course, I'm drawing these blobs as nested inside of each other. They can actually be separate from each other as well. So now we go to the warm neutral medium. We're getting down in temperatures again. Cold neutral medium. We're getting colder and colder. And then the molecular medium. This is where all the star formers live in this plasma, right? And this is around 10. So it's actually really, really cold. And you can play the same games over here. As the temperature cools, you become denser and denser until you get down to like 10 to the square, 10 to the 6 hydrogen per centimeter cubed. And you can already kind of see that there's going to be some inverse relationship between the amount of mass in the ISM and the volume in which the plasma contains, the phase, right? The volume filling factor of the phase. And in fact, what you find is for the WIM, you have around 20%-ish, 20 to 30% if the volume is in the WIM and the warm neutral medium. So these two mediums together. And by the time you get down to where stars form in the molecular medium or the molecular clouds, these tiny little clumps, you're only about 1% of the volume, but you're at a huge fraction of the mass. Most of the mass is in these tiny little clouds, but most of the volume is in the hot ionized mediums, warm ionized mediums. So what else can we talk about? Well, the Reynolds numbers for all of these are gigantic. So you get down to 10 to the 10 down here. Oops. I may as well write them all out. And we get to quite large RM. However, we start essentially running into other non-ideal effects that are not ohmic diffusion. And that's because when you get down to the molecular cloud scales in the ISM, you really are in a neutral rich plasma. So there's the ionization fraction, or the ion fraction rather, is around 10 to the negative 6 here in the molecular. So it means that you're in a very neutral rich, you have neutrals all around you. And your ions are essentially the things that are connected to the magnetic fields, right? So this tells us that flux freezing doesn't quite work. This allows us to slip through magnetic fields. So this is the ohmic resistivity. But if you have a neutral rich plasma, the ions are getting bumped into by all the neutrals and giving off the momentum to the neutrals. So you actually run into ambipolar diffusion effects before you get to the ohmic RM here. So I'm just going to put some dots here. because we don't really actually know what the RM is necessarily and what dominates. It's probably through neutral interactions on these scales. Yes.
At what point,
Beyond ohmic, as in ambipolar. I would say here.
Well, broadly, yes, but I was wondering if
No, I'm not going to be more specific. So we have a good idea that we have these gigantic RMs, at least on the small scales in the ISM, okay? So that means that a small perturbation to the velocities become nonlinear very quickly. So this is what excites the turbulence, right? The RM is very large, so any small perturbation to the velocity quickly undergoes a cascade. The dissipation is not killing off these nonlinear structures. So what actually drives the turbulence in the ISM? What is actually the source of these perturbations to the velocity? Well, there's a whole zoo of sources. Turbulent drivers. So the first one is, of course, supernova going off, injecting compressible modes into the media, detonating everywhere, right? They're just detonating like this in the ISM. And of course, as they expand, they stir the ISM, they enrich it with perturbations that can go turbulent, unstable. You have winds from massive stars. You have jets from massive stars. You have AGN feedback. You can just kind of keep listing these things out. And of course, these all inject both momentum and energy into the medium, not just one or the other. So what I want to say here, the last thing about all these different turbulent drivers, which I'm just going to essentially ignore all of these ones, is that from simulation, you get a stratified box, so a box with some scale height. You explode supernova in that box with some prescription based on the supernova rate in which they're firing off, just based on a Milky Way kind of analog rate. And what you find is that you can easily drive RMS velocities much greater than 8 kilometers a second, which is kind of the fiducial amount of turbulence, fiducial amount of velocity dispersion that you need in our galaxy. So my point is that with supernova alone, you can drive a sufficient amount of velocity dispersion in the galaxy. I'm not saying that this is the only source, but I'm saying it certainly just energetically can drive the turbulence that we see in our galaxy. Now, we should talk about turbulence. Like I talked about velocity dispersions. Velocity dispersions are completely insufficient to characterize turbulence, completely insufficient. And most of the people talk about, of course, K41. So K41 is Kolmogorov's kind of historical paper on turbulence, isotropic. So let's just list some assumptions from this model. So isotropic, homogeneous, local interactions. We'll talk about this in a second. And then assigned energy flux from L down to L prime, where L is greater than L prime. So as in, you push energy down to smaller scales in the Kolmogorov model. So pretty much all of Kolmogorov, you can derive all of Kolmogorov's results by assuming one thing, and that is the energy flux, which is just U cubed over L, is constant. So the energy flux on any particular scale L is constant. So what does this look like? Well, let's go to K-space, my favorite space. So this is the power spectrum of the velocity. So this is kind of a kinetic energy run. And the Kolmogorov idea tells us that if you have some driving on the large scales, we'll call this L naught, the -1. Then essentially that's going to create a cascade to smaller scales. It's going to go k to the -5/3. We all know and love this. And the cascade is going to look like this in energy flux. It's going to go from the top and it's going to go down, epsilon constant for all scales. So the amount of energy leaving this mode goes into this mode. This energy flux is constant all the way down. And you can see the way that I'm describing this is through local interactions. This mode talks to this mode talks to that mode talks to that mode, et cetera, et cetera, et cetera. A non-local interaction in this case would look like this mode, K prime, and this mode, K double prime, can talk to each other like this. Right? Does this make sense? So the cascade in the Kolmogorov model is this. It is this local energy transfer through energy flux from one K mode to the other K mode, okay? And of course, this is truncated at some scale, K nu. And we know exactly what that scale is. That scale just comes about from essentially setting this to 1, because on large scales, you're going to have Reynolds number much larger than 1. And as you go down this cascade, the velocity is changing. The velocity is changing, so the velocity is getting smaller. You can just see that because the slope of the cascade is downward. L is getting smaller. So at some point, you run into a regime where RE is equal to 1 on that particular scale. The viscosity dominates and you truncate the cascade. So I hope this is clear. So what you can see that the Reynolds number plays a particular role here, and of course it does. From very vanilla Kolmogorov theory, we know that this particular range from L naught to L nu is set by the Reynolds number. So the Reynolds number determines the size scale of our cascade. And of course, with these size Reynolds numbers means we ought to have a large cascade in every phase of the ISM. I hope that is clear. Now, I talked about assigned energy flux, which isn't quite so obvious just from this little derivation here. So there was some really work done back from K41, B. So this is his second paper. This was his first paper, just describing the cascade, describing his, K to the -5/3, blah, 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 blah. But there's a very beautiful result with the third moment of the velocity fluctuations, and that is this. Very, very simple. There should be L here. So this looks a lot like a U cubed. This looks like a lot like an L because it is exactly an L. And so it took maybe 30 years, but we got a different form of this that makes it even more obvious. So this is now the divergence delta U as a vector, delta U squared, is equal to -4 epsilon. So this is the energy flux, this is the energy flux. So what is this telling us? Well, this tells us, so this is a positive quantity, this is a positive quantity. This tells us something very interesting here. It tells us that so this is exactly energy flux, right? This is U cubed, this is 1 over L. So this side of the equation is exactly energy flux, and it's equal to -4 times this constant energy flux that happens on each scale. So this tells us something very important here about the Kolmogorov theory. So if we have a scale of L, then we go to a scale L prime, which is smaller, obviously smaller. Then what the turbulence cascade wants to do is it wants to essentially it wants to be convergent. It wants to push energy down. This acts like a sink, right? This is negative sink. The energy flux goes down into the scale. So this is telling us the sign of the energy flux. It tells us it goes from large scales to small scales, and it acts like a sink. So the energy flux acts like a sink in the Kolmogorov model. It goes down scales. It goes down. So this is called Kolmogorov K41's 4/5 law, which is kind of less known, I would say, in astrophysics, but it's super important. It tells us the sign of the energy flux in the Kolmogorov model. It goes down. So I hope this is clear. What was that, sorry?
Can you explain the notation for the divergence?
Oh, so this is the divergence computed on scale L. As in, like, I'm computing divergence on each one of these scales.
But then, should there be some average somewhere?
No, these are all on scale L's as well.
Okay.
Yeah, everything is kind of on scale L. This is actually also on scale L.
Sorry, I had a similar question. When you say on scale L, you mean something like an isolated load around a particular.
Yes, so
Back into real space, and then you do operations like this.
yeah, essentially you have to think about defining a fluctuation on this particular scale. Delta UL is equal to U R plus L minus U R. So it's a fluctuation defined on that scale, on this scale. And then if this is homogeneous, right, then it means that this R doesn't matter at all. You can pick any R. And if this is isotropic, then you don't even need to worry about the directionality of the scale. You can pick any L. You just care about L magnitudes. Does this make more sense? Yes, so you have to define this gradient operator in a similar fashion, which just means taking gradients on this scale.
Hi,
They've just taken her in
I hope that's
for
not confusing.
an
I
X-ray.
hope you can at least understand it conceptually.
X-ray. Okay.
Yeah.
All right.
Well, that's faster.
So my
than
whole point here
an MRI.
is,
Right, just going to ask one question.
yes, yes.
So, you still have your delta U as a function of, so I'm thinking of like a velocity field.
Mhm.
And I have a velocity fluctuation field, which is delta U.
Mhm.
Is that right?
Mhm.
Okay, so now you have a coordinate R, and then I smooth that whole field over the length scale L,
Yeah.
and then take the divergence of that whole field. Is that what I should expect that to be?
So I think in terms of calculating that, that's true. It just, this is an analytical result that comes essentially from rearranging this to some degree, right? And you can see that what you have is essentially this average over L. You bring the L over here, and you already get something like a U cubed over L. But what you actually want to turn this into a differential operator on this particular scale L, and this is what this is meant to represent.
Yeah,
How you compute it, I would actually do, like you want to do this in real space, obviously, you don't want to do it in K-space.
Yeah.
I would do a Gaussian smooth of this scale L and then take the divergence on that scale.
Right.
Take a kernel, pick out that L, take the divergence on that scale.
Yeah, okay. Yeah, I guess it's not
I'm actually going to show you how to compute this in K-space.
cool. It's just not clear to me how second thing is very natural. I mean, like basically, I think the argument you're trying to make is you promote 1 by n divergence like operator.
Yes.
I just don't understand why that's.
So this is the paper that you should read, Monin and Lag. Lawn, 1975. If you're interested in the exact definition of this particular operator. But I hope it's conceptually clear. It's meant to, all I want to get at is that that the energy flux acts like a sink in the Kolmogorov model. So you go from large scales to small scales. You push energy down the cascade. So that's all I wanted to say about that. The other final thing that I want to say about energy flux is that if we want to actually test whether something like this multi-phase medium that is undergoing all these different energy injection processes is Kolmogorov in nature, it is not enough just to look at the spectrum. We should actually turn to the energy flux. It is the energy flux that tells us information about the Kolmogorov model. Kolmogorov's model is all developed directly from the energy flux. So let's talk about how to measure the energy flux for a given stochastic velocity field. So we want to set up a kind of mathematical model that allows us to extract particular K modes from this turbulent process and then interact it with other K modes, okay? So the first thing that we should do is we should develop a filtered field. So a filtered field as in like, I'm going to filter it over a particular K mode of interest, K prime in this case. We are transforming my field of interest, selecting a K mode or a shell of K mode. To play with. So this is super simple. Everyone can get behind this. But what I want to do now is to actually rewrite out the momentum equation where all these terms come from in terms of filtered fields. Okay, so let's write down the filtered momentum equation. This is my real space coordinate.
Yes, is that the exponent should have as well, right?
No. L prime is just
Oh, okay.
Yeah. So let's write down the filtered momentum equation. I'm using the same prime notation here. It's actually super simple. It's pretty much exactly the momentum equation that we all know and love. Everyone knows the momentum equation, right? And everyone loves it. So I'm really just propagating this filtering through my momentum equation, where here is my gravitational potential, great point. And then here I am going to have some supernova source term as well. Why not? Momentum injection, this should be a rate. So this looks super simple. But now I want to multiply this equation by another filtered field. So I'm selecting, let's say, a K mode right next to it, and we'll call this K mode prime prime instead of just prime. So that's super simple as well. The last thing I'm going to do this in one step, is I'm going to multiply by another filtered field. So this exactly, but with a different K mode. But then I'm also going to average the equations. So what you're going to see is that I'm going to get something like this. U prime, U double prime. And this looks exactly like a correlation function because it is a correlation function. So now we're actually investigating the dynamical evolution of the correlation function. And in particular, this gives me these really nice terms. U double prime. I'm going to use the tensor product notation. So this is just Ui, Uj. U prime double dot. So this is the dyadic product. So this is just the double dot product. U prime, like this. So this is my first term. And this is actually just the advection term. This is this term. But now I'm looking at the interaction between this U prime mode and this U double prime mode. I hope that makes sense. I can keep writing out all the other terms, but I don't think it's even actually very important. This term already is looking very promising. It's a U cubed over L term, of course. And the way to think about this term is that this term is the energy flux transfer from the U prime into the U double prime, mediated by a third mode, U. We haven't specified what that mode is. It could be any single mode. So we don't actually localize this interaction, but we localize the energy flux. So there's energy flux moving between these modes. It's all captured in this term right here. It goes from U prime into U double prime, mediated by U. That's the way to think about this three-wave interaction.
You also a filter field?
No, well, the thing is, you can write this down for triply filtered fields. So I also would have a U triple prime here. It ends up being very similar. And then we also would be able to localize what mode is interacting with U prime to give energy to U triple prime. But I'm not interested in that. I'm saying this makes it a three-dimensional problem. So I'm just keeping it 2D here. And all I want to know is where the energy flux comes from and where it goes. I don't care how it interacts, right? So that's exactly this. That's exactly this. I'm taking some K prime and asking the question, where does the energy flux from K prime go? Does it go to here, K double prime? Does it go to here, K triple prime? I don't care how it gets there. I just want to know about there to there. Does that make sense? And it reduces the dimensionality of the problem because you can imagine you have like, what you want to probe now is all prime, double prime modes, right? You want to probe over all their interactions. There's one further thing that I want to do just to prepare you for what I'm going to show you on the projector. And that is, so we have our classical Kolmogorov interaction. It's right here. So it looks like this: U double prime tensor product, oops, U prime grad U prime, like this. Now, what I'm actually interested in the case of supernova turbulence, is the nature of the compressible modes versus the incompressible modes. So supernova explode with energy that's all in the compressible modes. The Kolmogorov cascade is an incompressible cascade. And then the divergence of all of Kolmogorov ideas are exactly zero. So somehow, if we want to establish that there is a Kolmogorov-like cascade in supernova-driven turbulence, we also have to talk about the two different types of modes, the compressible and incompressible modes. And so I can write down the transfer functions because I can rewrite every U here in terms of a compressible and an incompressible component. And I can do that via the Helmholtz decomposition. For those familiar with it, you can take any smooth vector field and turn it into compressible and incompressible components. S, I'm going to say S for solenoidal. And of course, this mode doesn't have any curl. So there's no curl in this mode. And this mode doesn't have any divergence. So you can make this calculation. It's very simple to do in K-space. So that gives me, from this one particular transfer, it gives me a range of transfers to deal with. I'm going to use this notation here. It's going to be transfer function from compressible to compressible, mediated by a compressible mode like this. And that's going to be equal to, of course, minus UC double prime, tensor product UC. Again, we don't really care about the locality of the interaction. Gradient tensor of UC double or single prime like that. Just to give you another example, USSC is going to be equal to transfer from this, transfer into a solenoidal mode, mediated by a compressible mode from another solenoidal mode. So when I have two like modes on the bottom, that's probing inside of a cascade, right? Like the cascades you can break up into compressible and incompressible modes, and then any CC or SS on the bottom means that you're looking at mode interactions within that cascade. So is this notation clear?
functional dependence of these vector sizes just L prime and L double prime?
Yes,
Also,
exactly.
L.
I would say K prime, K double prime.
Why is there no dependence on the UC? Like, so,
As in the mediating mode?
yeah.
Well, I've integrated it out. That's the way to think about it. Because for these filtered fields, obviously, if I sum over all of the filters, so this is summing over all of the K primes, I get back my regular field, right? Think about what I've done here is I'm integrating over all filters for the U mode, which means I localize the interaction, but I can still localize the energy flux.
Is that what you're doing with?
Uh-huh.
Are you saying the brackets are doing that? Like, what's the, like, which equation here is, are you integrating it?
Well, actually, you have to go back to here.
Okay, cool.
You have to go all the way back to here,
Yeah.
and write out all of these filters with a filter for this mode as well. And then the integral comes into there. Then you have to integrate this equation to get rid of that dependence. Yeah. Yeah.
So the incompressible mode, when we think that the vortex like this,
Uh-huh. A vortex-like basis instead of a Fourier basis. Well, the Helmholtz decomposition is.
Oh, that's sure in real space. But
Yes. You can do it equivalently in K-space. Like,
what I'm getting at is,
let's talk about this after because I want to push into the results. So we just did all this work. I'm very sorry, but I wanted to show you how to get to this particular equations to probe the energy flux. Both of these are energy fluxes, right? These are all energy fluxes from compressible to compressible, from solenoidal to solenoidal. So we're going to use these tools in a simulation to understand what supernova-driven turbulence is actually doing. And we'll be able to use them to exactly probe, is the cascade in supernova-driven turbulence like this? Is this what's happening, right? Because we actually get the energy flux for every single K-mode pair. This is cool.
The usual, like, Kolmogorov thing. What is
Let's show you right now. We'll start with the simple turbulent box, and then we'll go to fully supernova-driven turbulence in a stratified cut out of a galactic disk. Boom. So this is a fantastic paper if you want to learn more about these particular types of transformations that you do by turning your underlying MHD model, HD model into a set of transfers. Now, the first thing you can test is essentially is the energy flux. So this is kind of just those transfer functions as a function of K. When you sum over all the transfers, does that change as a function of K? And you can see in a very simple turbulent box, this is just an MHD turbulent box, that you get this region where the transfer functions are constant in energy flux. So that's exactly what that's exactly what Kolmogorov wants. He wants that the energy flux is constant, okay? Now, this is a really cool plot. So what you're seeing here is the K prime to K triple prime. Sorry, the notation has changed between the board and the slides. This is like a K double prime. Plane here, okay? So you're seeing a plane. And essentially the way to interpret this plane is that the blue is energy flux leaving that mode. The black is the mode that we're interested in. So we're interested in the modes along the diagonal. We're asking the question, where is the energy flux coming in to this mode? And where is the energy flux leaving this mode? So blue is energy is leaving and entering the diagonal mode. Yellow is energy flux leaving the diagonal mode. So in the Kolmogorov picture of turbulence, this should be all tightly around the diagonal, right? This is local transfer. This is that. This is this mode speaking to this mode speaking to this mode speaking. This is the cascade in terms of energy flux. So this is what you have to show me is happening in your simulations if you start talking about turbulence. Okay. But let's do a more realistic ISM. So here I'm just writing down the hydrodynamical model. Hydrodynamics, as in there's no magnetic fields, which is really sad for me because I love magnetic fields. But here I just want to do something very, very simple. I have a static gravitational potential here. So there's a disk structure. You can kind of think about this as a slice of a galactic disk. There's no rotation. There's no background shear at all. I just want to isolate the effects of supernova-driven turbulence. And I have supernovas stochastically going off uniformly within 2 scale heights of the disk. So they're allowed to go off anywhere within the scale heights like this. And then what else do I need to tell you about this model? We go up to 1,000 cubed. I wouldn't trust anything beyond 10 PC. Why isn't it allowing me to go to the next slide? Here we go. This is just a little bit about the static gravitational potential. It has a stratified disk component, has a spherical halo component. The supernova driving prescription is actually based on a star formation rate from Milky Way kind of type galaxy, where one supernova goes off per 100 solar mass of star formation. So it's a simple prescription, but it allows us to test the effects of this type of supernova-driven turbulence, which I think is fine. There's cooling and heating, of course. So we have a multi-phase ISM here. This is the pressure and the density plot. Essentially, our cooling function, these are all the terms in our cooling function. Our cooling function kind of cuts off at 10 to the 4 Kelvin. So it means that we don't have a self-consistent cold gas phase in the simulation. And the reason for this is just because I wouldn't have resolution to actually resolve that gas phase anyway. So really, I'm just talking about kind of hot and warm turbulent dynamics of the disk. And that's really all I resolve at 1,000 cubes for this particular simulation type. Now, the gas obviously gets to, so this is a isotherm, a 100 Kelvin isotherm here. The gas does actually get to colder places in phase space, and that's just because as the supernova expand, they cool. So there's this adiabats, there's all these adiabats that take you down to colder regions in the gas, colder than 10 to the 4 Kelvin, just through adiabatic expansion in the simulations. So we drive this, we drive. We drive the, just with the supernova going off. And here I'm just computing the Mach number. And you can see we go through this transient phase where the Mach number goes through the roof, and then it comes back down and it gets into quasi-steady state. And so any of the statistics that I'll be showing you are from averages from multiple realizations in this steady state, just to make sure we aren't sensitive to any kind of intermittent fluctuations, which are prevalent in supernova-driven turbulence. Of course, you can see just how these little spikes there are. And this is just from supernova going off, especially far away from the disk at that 2 scale height kind of hard limit that we have. They'll really change the velocity dispersion quite drastically there, which changes the Mach number, of course. This gives us, essentially, we can work out from the effective scale height that we have set versus our velocity dispersion, we have like a 80 mega year turnover time at the scale height for the turbulence. Let's just very briefly talk about power spectrum, because if you're a turbulence theorist, this is what all you've worked with for a long time. We separate our power spectrum up into perpendicular and parallel components, but here I'm just plotting the perpendicular. So that is that you have some domain decomposition based on the disk, right? The disk has some orientation, so you can talk about modes moving up and down the disk, or you can talk about modes moving around the disk like this. Now, the perpendicular and parallel end up being pretty similar, so I'm not going to talk about the differences between those two directions here. I just want to talk about the power spectrum in general. So power spectrum in general look like Kolmogorov. Wow, I've got Kolmogorov turbulence. Wow, let's finish everything and move on. But if you actually do the decomposition into compressible and solenoidal modes, as I was talking about down here, then you immediately find, so this is compensated by k to the -2, that the compressible modes follow a different spectrum, a k to the -2 spectrum, through a significant amount of range here. This line here is where the energy flux is rather constant. So this is where our cascade would be. And the incompressible modes keep going. They like k to the -3 half-ish. So already you see differences between what the compressible modes are doing, which are sourced from, of course, the exploding supernova, and the solenoidal modes are doing, which are sourced from presumably interactions between shells, post-shock regions in the supernova, et cetera, et cetera. But there's some differences, is my main point. Now, let's actually have a look at the transfer functions. This is where it gets really interesting and why we did all this work on the board. So I have used the correct notation here, or the same notation here for the transfer function. I have used, unfortunately, different notation here for the prime and triprime, okay? But still, same deal as before. So this is the compressible mode to compressible mode transfer. So you can think about supernova shells maybe interacting with each other here, or a shock turning into a bunch of shocklets. And what you find here is that you actually do have a very reasonably local cascade. And this is when it's mediated by an incompressible mode. So the compressible mode in that spectrum we were showing really is like a local spectrum when you are mediated by a solenoidal mode or an incompressible mode. Now this looks a little bit different when you go compressible, compressible, mediated by compressible. Now you can see some non-localities kind of creeping in here. So this mode right here is getting energy up all the way from this mode over here, putting energy into this. And this mode here is dumping energy all the way down to there. So there's non-local effects happening in these transfers. So at least the way that I've thought about this, and I haven't thought about this in such detail as I have for the other transfer functions. But you can kind of think about this compressible interaction like this as compressible modes kind of surfing down post-shock regions. So here you're seeing essentially the compressible contribution to the vorticity. So this is the interaction between the compressible modes and the vorticity. And you see that the post-shock regions kind of behind the supernova as they're expanding are just bright here. So that's a lot of interactions between compressible and solenoidal modes. So you can kind of think as they kind of scattering off all these solenoidal, the compressible modes scattering off all these solenoidal modes that are developing, they go down the cascade in these post-shock regions. The compressible mediated by compressible, I think about it as interaction between all of the expanding supernova remnants, where you get all these kind of crazy small shocklets developing. But this is actually not even the interesting part of this.
Okay.
Yes.
Some of these remnants are filled, others are empty.
Yes. Well, this is a slice. So in 3D, they all look filled. You're kind of just slicing it in 2D. You see different MRI slices of the shock. So what are you actually saying? Are you saying that there's just a void here?
Yeah.
Well, this void is because there's no interaction between the vorticity and the. Yes.
Why are some different?
So they're older. There's just there's an age distribution. Some of them are actually going off. Some of them are actually completely turned off and undergoing cascade down. So some of them are expanding. They're new. They're young, and some of them are already got to their full size, and they're just. Mm-hmm. But this is, by the way, slicing at this supernova. You can imagine is. Yeah, yeah. Well, it depends, because if you're just slicing through this, because this is expanding shell, you have actually a cooling region here. So there is cooling going on here, which is what separates the shell from the vorticity. So this big empty part is just an old remnant that has all the cooling going on in the middle, and it just still has a blast wave, just kind of momentum, just kind of leaving the medium like this.
Okay, but this one where you have the arrow pointing to that middle top.
Yes.
And it looks like there's some interior structure there where that's due to cooling.
So this interior structure is to do with cooling. This So this is hot gas. Oh, sorry, this is hot gas. This is cold gas. This is cooling. It's actually the baroclinicity. Anyway, what I really so just to summarize these transfers, the compressible mode transfers here, is that you have direct cascades, surf down post-shock regions, and then you have kind of all these shock interactions giving rise to these more non-local transfers. But what becomes very, very interesting is now we look at the incompressible transfers. So incompressible transfers are, of course, they should be like this, right? This is all incompressible transfer. If the supernova-driven turbulence is anything like Kolmogorov, it should show up very clearly in these transfers. The first thing you see, so this is the classical Kolmogorov transfer. So it's solenoidal, solenoidal, solenoidal. So these are all just incompressible modes interacting with each other. And you see that is quite non-local. So it has these broad wings at low K, so at large scales. And then it becomes more local as you go to small scales. But the point is that this is rather non-local. This is a non-local transfer of energy in this particular transfer, dominated by this non-local effect. Now, the really interesting transfer function is this incompressible to incompressible mediated by a compressible mode. So you can see, let's just ignore this. You can see that there's a direct component, so the cascade is going down, but here, everything flips. So the red is on this side now, and the blue is on this side. So that is a cascade, a very local cascade that goes up. It goes this way. So here is the first evidence for an inverse cascade in supernova-driven turbulence.
Are you worried? I mean, I would think for low enough K values, there would be some kind of noise.
For low enough or high enough?
Low, right? I mean,
Low is fine. Low is fine. The numerical effects happen at high K. Like I wouldn't trust anything beyond here, like this way, because that's numerical dissipation.
oh yeah.
This is fine.
I just meant like for a given box size, you would have less number of like.
Oh, as in sampling the
Yeah,
low K
sampling,
modes.
yeah.
No, I'm not super worried about that. When I look at the power spectrum that I showed you before, and I look at the 1 sigma fluctuations, there's no systematic change across all modes. If there was large systematics at the low K end, I would be more worried. So this is really cool. So, you know, what I'm showing you right now is that in the Kolmogorov transfer function, the incompressible, 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 you have a rather non-local cascade that then turns into a more local cascade at smaller scales. But then in the solenoidal compressible, you have these two cascades happening at the same time. You have an inverse cascade that happens, pushes energy flux, pushes energy, incompressible energy, to large scales, and then you have a direct cascade as well. So you have these two cascades happening at the same time.
What is the scale of the input?
The scale of the input energy is like here, right? It's a supernova. It goes off on the smallest scales. So we pick like 3 grid cell cubed. We inject our energy there.
That is cascading towards when it's starting to.
Well, the point is that for the solenoidal modes, we don't inject any. There's no injection of solenoidal modes. It's all compressible modes. And for that first little part of the supernova expanding, it isn't undergoing any kind of cascade at all. It's just an expanding, and then it's depositing energy. And as it deposits energy, this kind of stuff can happen. So let's work out, actually, just to finish this talk off, work out what this even is. How do we have an inverse cascade? So what you can do, which I think is really, really cool, is you can take all of the modes that are participating in the inverse cascade, and you can plot them in real space. So this is the real space plot of everything that's in the inverse cascade. And what you find here, and here in this case, I believe that, oh yes, so orange is the energy flux is going up to large scales. So it's doing this. blue is energy going down. And what you find spatially is that the energy cascade is upwards and downwards all over the place, right? It's just that on average, so we have to integrate over this entire plot to get 1 point, right? On average, it's going up in these particular scales. But spatially, it's going up and down everywhere. The cascade is really inhomogeneous in energy flux, which is really cool. And what you can work out is that you have an inverse cascade from young supernova detonating going off. They have a lot of divergence. They push things out to larger scales. You have essentially these incompressible modes surfing on supernova as they expand. And you can imagine those modes are going to lower and lower K modes as they expand like this. And then you have the older supernovas essentially expand all the way out and now just decaying. And they decay through their post-shock regions. They have this direct cascade that goes down, and you can actually see this convergence exactly as you would expect from this kind of relation. So let me just say my final thoughts. When we do the compressible mode interactions, we find direct cascades of compressible modes. This was actually also not really predicted by Kolmogorov. Kolmogorov is an incompressible theory. If anything, they should be passively advected by the incompressible modes. We don't find that. They undergo their own cascade. And then in the incompressible mode interactions, we find it inverse plus a direct cascade of solenoidal modes. So this is very, very non-Kolmogorov in nature. Very different from this, which is the background image of a energy spectrum. So long, K41. That's the end of my talk.
So this fact that this inverse cascade is not.
No.
But isn't it like you are like a supernova is heating energy in small scales and get that on larger scales. So in that sense, it seems intuitive.
It does, but what matters is where it's generating the incompressible modes, because people kind of had in their mind that they expand, they interact on large scales during this expansion, which then forms a direct cascade. This is not what happens. They take modes from small scales, bring them up with them to large scales, which can then feed the direct cascades. So there is an actual inverse cascade component. And it actually goes all the way to the winds. You drive energy from in the disk all the way into the winds through the inverse cascade. Yeah.
Yeah, I'm not sure. So sorry, what's the difference between the two things?
The difference is, so you have this supernova going off, interacting on large scales. The supernova remnants interact on large scales, which trickle straight down. If you want to hear about where because like I said, there still is, and something I haven't even discussed here, is where are the incompressible modes coming from, right? Because like I said, I'm driving with compressible modes from the smallest scales. Where do the incompressible modes come from? And if you want to hear about that, you'll have to come to Norm's group meeting tomorrow. I'll talk in more detail. But it is very interesting. It links us back to the multi-phase nature of the ISM. Through the multi-phase ISM, you can generate baroclinicity, you can generate phase mixing layers, and this is where all the incompressible modes come from. These phase mixing layers are actually right here. This is a fractal cooling layer, like I said, between the hot and cold. And this is pretty much to by many orders of magnitude the site of the generation for all the incompressible modes. So essentially the supernova have this fractal cooling layer between the two phases that they themselves develop through adiabatic expansion, and they bring that cooling layer with them to larger and larger scales, which is like the inverse cascade. They bring all these incompressible modes that they're generating the cooling layer to larger and larger scales that then are allowed to direct cascade. So another very interesting fact just comes about from where where do these incompressed modes get generated from? They actually don't get generated much by the interaction here. This is also very interesting. They get generated from the multi-phase component of the ISM. Yes, yes. So these pretty pictures are very early on in the simulations, but in the steady state, it doesn't look anything like this. They're everywhere. There's just turbulent mess everywhere. But you can see the cooling layers. You can see the cooling. Yep, in the disk. And yes. So yes, I'm showing a lot of the first panel here just to give everyone a good intuition for that there are supernova in a disk. But you can see in the steady state evolution, it looks much crazier, right? These are the compressor modes, and you can see blast waves everywhere. These are the incompressible modes, the vortical modes up here.
What's happening in terms of
Oh, you're blowing these fantastic winds.
Yeah.
You can see this is the mass density, and you're just blowing these fantastic winds out here. You have outflow boundaries here, and you actually get mass loss. And, it's all I can tell you right now is I would have to correct these transfer functions to include the outflow boundaries, and the energy flux is low enough, so I don't need to correct them. That's all I can tell you. I haven't measured the energy flux out exactly.
Well, that's it, because the efficiency, of course, you're dealing with kiloparsec.
Yeah,
up and down,
1 kpc.
But still somewhat.
Yep. But yeah, exactly. So this was meant to be a wind study. But I've seen a setup similar. Explore 1 kpc cube, 2 kpc, and then like 10 kpc, and they didn't find any significant deviations in this region of disk statistically.
They increase the upper bound.
Yes, so I feel like the statistics are converged for this region of plasma. Yes.
No, I was just asking specifically about the energy flux out.
Okay, yeah. Like I said, this hasn't been a very wind-focused study at all.
No magnetic.
No magnetic fields.
You're not considering the cosmic grid.
Not,
Cosmic grid.
no.
Super bubble.
Yeah, no.
Actually, are you seeing-
I don't know. I don't think so.
And large scale shocks. I mean,
Yeah.
you must have actually statistics, some strength.
Yeah, yeah. I think you have to change your seeding mechanism to be more mass density sensitive to really get some big super bubbles.
That's a good point. So to do the statistics, I mean, that's one thing to investigate. That's the statistics of the clustering of the supernova.
Yeah, I have a student at UCSC working on that question right now. We're using 3 different seeding schemes to make sure nothing changes. That's that.